This is Chapter 10, Ionic Bonds and Formulas, Section 10.1, Ions and Ion Formation. Here's our objectives. Be able to explain why atoms form ions, identify the most likely to form the positive and the negative ions, be able to give the symbols of the main groups and their charges, and predict the charge on the ions based on their electron affinity, ionization energy, and their configuration. Describe what polyatomic ions are and give the formula of polyatomic ions, name them, and so on. So you can see there's a lot of things that we're going to cover in here. Some are pretty straightforward, others a little more difficult, but these are the things we're going to cover in this section. Most of the elements that you see, most elements exist as ions. You don't usually see them just as elements free in nature. And the reason is because they're more chemically stable when they are an ion than they are when they're just an atom. And matter is always trying to get to the lowest form of energy, and that's just the most stable when it's lower energy. So let's take a look at this. Here's an example of fluorine, and you can see on the left that's a regular fluorine atom. On the right we have a fluoride ion. And atoms become ions, as you recall. The reason that they become ions is they're going to gain or lose electrons. In this example, fluorine has gained an electron, so there's an electron that's been added in here. And so this is now a more stable configuration for fluorine. Cations, remember, are the positive ones, so we might have things like Na plus or Mg2 plus. Those are cations, they're positively charged. The negative ions are known as anions, so the one up above, fluorine, that's an anion, or we could have oxygen, which is O2 minus. Those are anions. And these changes will occur spontaneously if, a lot of times, there's a decrease in potential energy. So overall, these things will happen if, when they're done, there's lower energy than what it was when they started. So when this fluorine atom up above gets this extra electron, it actually gets rid of energy, loses energy, and has lower potential energy. So it's a lower energy state. Therefore, it's more stable. It doesn't take as much energy to hold it there. All right, so let's compare metals versus nonmetals. Metals, recall, are on the left side of the periodic table. They have low ionization energy, and remember, if they have low ionization energy, means it's easy to remove them. Ionization energy is how easy is it to take an electron away. They also have low electron affinities, which means they're not attracted to new electrons, so they're not trying to get new electrons. So it's easy to remove one. It's hard for them to get a new one. So these guys tend to lose, not gain electrons. Nonmetals, on the other hand, are just the opposite. They have high ionization energy. It's really hard to get take an electron away. And low electron affinity, it means they're really trying to get another electron. So therefore they don't lose, but they do gain. And noble gases have high ionization and low electron affinity, which means they don't want to gain or they don't want to lose. They are just happy the way they are. All right, so ionization energy, remember when you have taken all the electrons out of that outer energy level, then the next one jumps drastically. So when we start to take electrons away, there's always a certain amount of energy required. But when you're trying to take that one out of a full energy level, that takes a lot of energy. So for instance, when we're talking about magnesium, it's not too hard to take this guy away here, this first one. It's not too hard to take that one away. It's not too hard to take that one away. And then once you've done that, you've taken away that outside level. But to take the next one inside away, that's where you get this big jump. And you can just look at ionization numbers on a chart, and you can tell what group an element is in based on the fact that, hey, after this, this one might take, a decent amount of energy. This take a little bit more because the second one's always more. But this one takes huge amounts, and so you know that it's in group 2A. It'll easily lose 2 electrons, but not the third one. Now, a lot of times, rather than drawing out all of those rings and everything, we'll do it as Lewis structures. And let's take a look at fluorine, and we're talking about it in terms of electron affinity. Fluorine, we said, has a high electron affinity. It wants to get another electron, and it's got a space for another electron. So it's going to, there's another atom running around that's got one that'll easily lose it, like sodium or something like that. It's going to take it and make this and fill in its shell. And here we have the fluoride, and actually I should put in a negative sign because it's now negative. It has less potential energy than the one previous where there was only 7 in the outer level. Oxygen, it has high electron affinity, and it has space for 2 more electrons. So it's going to try and find 2 extra electrons to fill in its outer level, and that makes it a very stable configuration. So group 1A, here's our elements, typically lithium, sodium, potassium, rubidium, cesium, francium. These guys all form +1 ions. Now hydrogen is in that group. Hydrogen is a little bit different. It will act like an H+. It will be that way occasionally, not always. It will do some other things. So hydrogen, and it's not a metal, but hydrogen does act similar to those in this particular group. Group 2A, there's your group 2A metals, and notice that all of these form a +2 or 2+ ion. They will lose 2 electrons. Group 3A, these guys tend to form 3+ ions. They like to get rid of 3 electrons. Notice that we didn't really talk about boron here. That's the top one, and that's because boron, if you remember that zigzag line that goes through there, boron's on top of that. It's actually a non-metal, kind of more on the non-metal side than it is on the metal, and so it doesn't really lose electrons. It tends to share them, and we'll get into that in another chapter. So it usually is not going to be considered to be one of these ones that forms a 3+ ion. So it usually doesn't lose all of its valence ones. Group 6, here's our group 6 metals, and these guys now we have high electron affinity. They're going to attract 2 electrons. So you're going to form -2 charges, or 2- ions. And here's our typical ones: oxygen, sulfur, selenium, tellurium. Those are going to be the ones that we're going to talk about the most. Group 7A, once again, high electron affinities, form -1 ions. Fluorine, chlorine, bromine, iodine, those are the ones that form those ions. Remember, and just to recall that anytime that these are negative, these ions are now called, they all end in IDE. So while it was a fluorine atom, it's the fluoride ion, the chloride ion, bromide, iodide, and so on. Okay, so those are simple when you're talking about just the basic elements, that they lose or gain electrons and form their ions. But there are also these things known as polyatomic ions, and these are a group of elements. They work together. They're bonded covalently, which we will talk about in the next chapter. We'll get into that in a little bit more detail in that chapter. And they behave as if they were just a single ion. So let's just take a real simple one. Let's say we're talking about NO3 minus. This is known as the nitrate ion. So this thing right here acts as one ion, and NO3 will stay together throughout the equation, throughout the reaction. That NO3 acts as one particular thing. It has a charge of -1, and this is known as a polyatomic ion. We will be having a quiz on these polyatomic ions, these 10 that are right here. You will need to learn those. We'll use polyatomic ions quite a bit, and these are probably 10 of the most common ones right here. Notice that most of them are negatives. The only exception to that we have, there are some others, but the main one that we're going to talk about is ammonium. Okay, so that's a positive ion, it's a +4 ion, but all of the other ones are negatives. And make sure that you note how this works, okay? So let's take a look at this acetate ion. That's an O2. The 2 stands for the oxygen, not the charge. It's a -1 charge. There's only one negative sign up there. So it's a C2H3O2. That means there's 2 carbons, 3 hydrogens, 2 oxygens, but it has a -1 charge overall. So this whole thing here has a -1 charge. Notice that you have ones like CO3, so there's 1 carbon, 3 oxygens, but together it has a -2 charge. So this is the ion, the CO3, those are the elements. This is the charge that goes along with it. Okay, at this point, we kind of covered this stuff, and you could quit this. What I want to spend about probably 4 or 5 minutes talking about is kind of how to help you learn these particular ions, kind of tell you some key things about them. But if you think, hey, I can just look at those and memorize them, you're welcome to just stop the video at this point in time because we're pretty well done with anything new. All right, so let's talk about, first of all, there are 3, if you notice in this chart, most of them end in ATE, okay? They're 8s, okay? There are 3 that don't. And so let's kind of, typically on a lot of polyatomic ions, you're going to see these kind of endings. You're going to see 8s and ites. Those are pretty typical. 8, all of this has to do with how much oxygen and things they have in these compounds. But in general, anything with ite is going to have 1 less oxygen in it than the 8 version. And we don't have too many examples of that here, but if you look at this one down here, the sulfate and the sulfite, notice that the sulfite has 1 less oxygen than the sulfate. Okay. So when you're thinking about these, if you're confused as to what you're naming, most of them end in ATE. And most of them start with the compound, or the element actually, that we have. So let's take a look at some pretty common ones. Carbonate, okay? So it's a polyatomic ion, carbon 8. Chrome 8. Now this one has 1 chromium atom. This one has 2, so it's known as the dichromate ion. And, is there any good, easy way to remember all this? No. It's called, you just got to memorize a few of these things so that you can use them. These are kind of the key ones. These are the ones that you should know, and so on. The exception ones, ammonium obviously is kind of the most unusual one in that it is a positive one. And this is not ammonia. So like when you think of ammonia like the cleaning product or whatever, this is not ammonia. Ammonia is NH3 and it is a compound, not an ion. This is NH4 plus and it is an ion. And there's a difference there. Make sure that you're aware of that. The acetate one is a little bit different. C2H3O2. I don't know of any good easy way for that. Hydroxide, this is another one to be aware of. This is one of the few polyatomic ions that end in IDE. Typically, an IDE ending tells you that you have a binary compound, that you have 2 different elements, not a polyatomic ion. This one is one of those bad ones that's an exception to that. And this is probably one of the most common polyatomic ions. So definitely know this, OH minus. Okay. Phosphate, we're looking at phosphorus and changing the endings to ATE. So you can see that probably on, these 3, if you think about naming them, and probably at least for sure these 2, you can take the element name, add in 8, and get what the name is. Some of the other ones are just going to have to kind of do flashcards or something to kind of memorize those. Be a little quiz where I'm either going to give you the name, you write the formula, or give you the formula, you write the name. And that is the end.